So the debate wages on every year about who is the best baseball players out there. So here's some data going back a long ways of batting averages. So we got batting averages from the 1910s, 1940s, and 1970s. So as we look at those, we say, okay, well the batting average for the 1910s is 266. The average of all players from the 1940s was 267, and the average from the 1970s is 261. And then every, grandpa, aunt, uncle, father, mother, whoever's a big baseball fan is wondering, well, so-and-so is a way better player than so-and-so. So we got Ty Cobb, Ted Williams, and George Brett, who each had great batting averages. So like Ty Cobb, his overall batting average was 4.2. So 420 times out of 1,000, he was getting a hit. Ted Williams was 406. And George Brett's was 390. All right, and so you just look at that and say, well, obviously, people say, obviously, Ty Cobb's is better because it was higher. But you also look and say, but the overall average was lower. So does that mean he was higher relative to the others? But then you got to look at, but how spread out was the data? While this is higher than 266, is it significantly higher than the 406 is above 267 based on how spread out the data is? And then vice versa, and then correspondingly for 470. That's what this whole idea of relative standing is about, is if you want to compare apples to apples, well, sometimes you always don't have apples. So you have to find another method for comparing all of this information. And that's why we have standardization scores, or z-scores. So again, the formula for z-score is z equals x minus mu over sigma. So what I'm going to do is I'm going to then find the z-score for each of these. Now I'm going to do it, and I'm going to write the number in there. I would expect that you are grabbing your calculator, putting the numbers in, and finding these same values just to make sure that you are getting the same numbers. So go ahead and hit pause and and calculate out what each of those z-scores is. Don't forget though, going back to algebra here, it's not written, but there is a parenthesis there, so make sure you do that. Hit pause and then replay, and all the z-scores will show up. So hit pause now. Boom, there's the z-scores. So when you're looking at this and you go, okay, so what does this mean? This is what it means when it says, compare these people based on their relative standing. So relative standing means I'm thinking about z-scores. Ty Cobb has a z-score of 4.15, which means he is 4.15 standard deviations above the average. Because it's positive, it's above, and it's 4.15 standard deviations above the mean. So relative to everybody else, he's 4.15 higher, standard deviations higher than the mean. Ted Williams is 4.26. Wait a second. Lower number, but higher z-score. Well, that's because the spread is so much different. This one has a much larger spread, which means there's much more variability. So if I were to make a hypothetical graph of this one, the top one here, let's say it's normal and it's really spread out. Okay? Whereas the 1940s, it's going to be narrower. So what that means is a score that's above here versus above here, oops, I missed. Well, here, this area is smaller than this area. Now it's not a whole lot smaller because these numbers are actually go quite out there quite a ways. But when we talked about density curves, the proportion of the area above here is smaller than that proportional of area, even though the number itself is lower. So that's what we're getting at. So relative to the decade that they were in, that they were baseball players, Ted Williams, relatively speaking, was a better batter, had a higher batting average than the others, even though his number was lower than Ty Cobb's. All right, so Ty Cobb was amongst other baseball players, so we compare him to everybody else in that decade, Ted Williams to everybody else in that decade, and Ted Williams was a better baseball player compared to his counterparts during the 1940s. Now for this class, you do not have to know calculus, but if you did, so I'm going to draw a normal curve. If we did know calculus, the reason and the purpose of calculus is to say, okay, from here to here, what is the area underneath that curve? This is really a lot of what calculus does. So they find the equation, they do it out. So what they're actually doing in calculus is they're finding little rectangles, and their area of a rectangle is base times width, or base times height, or however you want to think about it. All right, and then they say, well, what happens if we make all of those smaller? So instead of 1, now we split all of them in half, and then find all those areas. And then we keep getting smaller and smaller and smaller, so as you zoom in and in and in, these are all getting to be almost so that they're on the curve. And they're going all the way down, each of them. So that's the purpose of calculus. We don't care. So while this is here, we really don't care about any of that. And get rid of that. It's all deleted. So what we really care about, though, is the fact that there are certain things about certain distributions, and I'll introduce this real quickly. So if something is a normal curve, it is centered at the mean, and what I always do is I draw my graph, and then I make 3 marks, or put my middle in there, label it with the mean, mu, again, M-E-W is kind of how you say it, mu, and then I mark 1, 2, 3 to the left, so that almost everything is between those 2, 3 endpoints. So this point here, because it's 1, 2, 3 below, now each of these is a standard deviation. So this width is 1 standard deviation. This width is 1 standard deviation. So they're all supposed to be the same width, even though my drawing might not. So each width. So this value right here is actually mu minus 3 sigma. And this value up here is mu plus 3 sigma. All right, pretty soon we're going to be talking about what's known as the empirical rule. The empirical rule is basically a guideline, to less than a rule, more of a guideline, that tells us, well, if starts with the big if the distribution is normally distributed, then there are certain characteristics that are true of normal curves. One of those is that in between mu plus sigma and mu minus sigma, in here, if I have a normal curve, generally speaking, that area is 68%. And there's more that we're going to learn about the empirical rule soon enough. But for now, that will do it. Let's see, reflection response. Why don't you tell me, no, go ahead. Ask me a question not related to statistics. Sky's the limit, doors wide open, whatever you want to know. Ask the question and I'll see if I have a response for you in class. That's it, folks.